Okay, so let us continue. So I guess I kind of reorganized this lecture, right? The slides, so it's kind of easier to follow and more organized, clearer, more details. So let's quickly go over this again. Nope, not this one. Sorry. Not this one. Right. So, right, again, the focus right here is about path probabilities, right, of a Markov chain with kind of application, right? Emphasis on tracking, right? A pattern, the first time to see a pattern in a Markov chain. Okay. So long story short, right? Suppose we have a very specific path, right? So I0, I1 up to IN here, right? Are states, right? So very specific, right? Just one path, right? One single path. Then the probability of this path, right, is, well, the probability you start there, right? You must start there, right? And this is the initial distribution times all the transition probabilities, right? Leading to the last state, right? And, right, this exactly, right, works by the Markov property and, right, the multiplication principle. And, right, to remind yourselves, right, the multiplication rule back in, I guess, lecture 1, right, tells us that to get the probability of a joint event, right, this is what we need, right? Well, of course, right, think of En as, right, now that you know, at that time I said, right, you know, so actually here, I think we have x0, right? So you could extend that to back to x0, whatever. But, right, at that time I said this exactly has a time flavor, right? So now you see what that is, right? But notice that the multiplication rule requires you to have the whole history, right? When you look at, let's say, the movement into the last state, right? And so that allows us to basically, right, drop the dependence, right, on the not recent state, right? Or basically the dependence only, right, is on the recent state by the Markov property, right? So that's what we have, okay? So that's it. So again, right, very easy, but just kind of, you know, remember that this goes back to, right, what we discussed on day 1. Okay, so, right, this is a specific path, right, focus on one sequence. While if you look at, right, p to the nij, again, right, this actually just moved from state I to state j, right, regardless of, right, so this actually is multiple paths, right, p to nij, right, all path at least from I to j, or if you want, right, this just says that, you know, this is just a particular example of this path, but less specific, right? Of course, if you know how to do this specific path, right, you can do like, you know, x0, x2, x4, x7, etc., right? You can skip in between, right? You just have to multiply the transition matrix accordingly, right? But just to remind ourselves, right, p, right, just kind of connect the two endpoints in n steps, right, regardless of how you move in between. All right. So last time we didn't have a specific example for P, right? So here we just kind of try to give an example, right? So this is P, right? And notice that here we call our states 1 to 5, so no state 0, right? This may or may not be, right, confusing, but you kind of have just to look at, right, the encoding to see if, right, there is a state 0 or not. So don't be confused with that. So this is, right, 1 to 5, doesn't matter, right? This is just example. So, right, so the probability of moving, right, from 2 to 3 to 4, etc., right, would be exactly like that, right? Assuming, of course, that you start at 2, right? So here we don't have an initial distribution. We just assume that we start at state 2 and moving on through this sequence of states. Right? All right. So that's the specific path, right? That's the easy part anyway, right? Any question about this? Okay. So now, right, the main technique or the main point that we want to look at, right, for this lecture is about avoiding, right, or entering a specific set of states, right, by a certain time. That set of state, right, we call, I guess, script A, right? And so the point, right, or the technique is to use a modified chain, right? We call W, that would basically has same state, right, with X that's outside of the class A, right, the class script A, and anything, right, inside class script A, we lump together, right, into an absorbing state called A, right, A for absorbing. And the transition matrix, right, for W is as follow, right? Again, looks scary, but it's not, right? Basically, it says that it's the same as P, right, for X, if you're outside the absorbing class. If you want to move outside absorbing class into the absorbing class, right? Then you just sum over all items in the absorbing class, okay? And then, of course, right, absorbing class is 1. And so here, right, is an example, right? Moving from P to Q, where we look at 3, 4, 5 as the absorbing class, right? So again, I think this should not be anything crazy, but just pause here, right, for you to take a look. So notice, for example, right, this block, right, namely the 1, 2, stays the same, right? And then, of course, these, I mean, the one here, right, becomes the 0.4 and 0.7, right? The rest are just a collapse into 0, 0, 1. Okay. All right. So the point, right, is that basically anything actually, right, having to do with this question will involve the modified chain W, right? So we just do this once and for all. Basically, right, we'll have a lot of questions, or we have varying types of questions, but they all will be addressed, right, by the by W. I guess sometimes we have to involve P back, right? So it will involve Q, right, and P, okay? So no need to redo this example many times. It's the same thing. Okay, so now, right, the first question is to move from I, right, into the absorbing class, right, or the class for some time before M, right? Then the answer is easy. It's Q to the MIA, right, where Q is the modified matrix, right? So I think, again, this is, by now, it should be an old idea. I'm just going to pause here to see if there's any question. All right. Another one, right, is kind of like similar, but now, right, we don't want to be in A, right? But we want to move from I to J, avoiding A during our trip, right? But notice here, I and J are both not outside of A, right? So in terms of our modified chain, sorry, in terms of our example, right? It's like we move from 1 to 2, avoiding, right? Let's say 3, 4, 5, right? On our path, right? We basically were asked, how do we move from 1 to 2? Meanwhile, right, always cycling between 1 and 2, right, throughout the path. Okay. Of course, you can also move from 1 to 1, right? That's okay, because 1 to 1 also is outside the absorbing class 3, 4, and 5, right? Again, the answer is simple. It's just Q to MIJ, right? Okay, any question on this one? Okay, so now, so that's almost basically it, right? Move along a path being in the class A at some point, or move along the class never in the class A, right? But there's some kind of, let's say, small technicalities, not big at all, right? It sounds like a big deal, but it's not. Notice that in all this analysis, it makes sense for us, right, to have I not in A or IJ not in A. Right. So let me pause here and see if you understand this. Why do we have to emphasize this? Is it necessary? Why do we keep harping on this in this calculation? Because, right, if it's not necessary, then the discussion below, right, is pointless. Why do we keep harping on this requirement? First of all, right, does it not make sense, for example, for me to, let's say, start at 3 here, right, and say 3, 4, 5 here? Does it not make logical sense to begin with? If it doesn't make logical sense, meaning it's nonsense, then of course, right, the question shouldn't even be raised.
For the question you just posed, that just gives you a probability of 1, right? Because
Incorrect.
no, okay.
That's no. Again, that's a good first reaction, but that's not wrong. The reason is here is x0, and this is 1.
Oh, I understand. Okay.
Right? So it's not a trivial question, right? I mean, like in the sense that you say the answer is obviously 1. No, not really, right? I start at 3, and somehow I end up at 3 at some point before 10, right? And notice that the trajectory can be something like 3, and then 1, 2, 4, and then maybe 3 again, right? Or sorry, if it's 4, then it's already there, right? Here.
But it's impossible to go from 3 to 1, correct? Because 3 is part of the absorbing class?
3 is part of the absorbing class of what? Notice, if you look at P by itself, is 3 an absorbing class?
No.
There you go. Again, right? It's just to tell you that this thing is subtle. We pretend, or we class 3 as part of the absorbing class in Q. Again, for the convenience or for the calculation of this type. Okay, again, contemplate that. Physically speaking, from X, that's what we call a modified chain, right? If we call it X again, that would be confusing. If we call this X here, that would be confusing. But no, right? This is a new chain that's just used, for calculation purpose, if you will, right? I mean, namely that these two probabilities are equal. But there's nothing physically, right, prevent us, or I guess probabilistically, prevent us to move from 3 to 1, let's say, in terms of transition matrix, right? It's possible. All right. So again, repeating my question, does this question make sense? Or at least it's sensible to ask this question? Like, it's some non-trivial probability. Is that true? If so, right? If you see that it's so, I'll take it as, no objection. If you have an objection, do ask. If not, then why do we have to make a big deal when we say this in these 2 slides? Any answer?
If I is already in A, we can't use the logic of our Q matrix and our new modified chain. We would have to come up with a different solution.
Agreed. That's exactly it, right? It's about the technicality. So basically, right, even though, right, there's nothing wrong with asking this question, the Q matrix itself does not see state 3, right? If you look at the Q matrix, it only has state 1, 2, and A. But it does not have state 3, because if you follow the answer, let's say you follow the suggested answer here, it will say something like Q to M 3A. And that by itself, right, actually it's not even a 1 like Kathy was suggesting. It's more like a nonsense, because 3 is not part of the Q matrix. Do you understand? So basically, right, it's about technicality, right? That our technicality here, because when we convert P to Q, we effectively do not see 3, 4, 5 as separate states anymore. So if anything we want to talk about in terms of 3, 4, and 5 at the beginning, at least, right? Of course, right? Notice this question again, as Kathy would have thought about, maybe if you have x1, then of course the probability is 1 because you're already there, right? But we start out x0, so that's kind of a separate thing. So, right, that's the point. That basically it still makes sense to ask questions about starting in those special observing class, right? But they will not, by technicality, be covered, right, by the Q matrix. That's why we have to discuss them separately. Okay. And I guess the name, right, kind of gives it away, how we handle. So let's see if you can guess what the technique would be. So what do you think, right? For example, let's take this question, right, just to make it easy. What if I is in A? For here, and J is not in A. So like, let's say this is I is 4, right? But J is 2. And this is 3, 4, and 5. How would that work? Can we still do it or no? The answer is yes, of course, we can do it, right? And the trick is actually very simple. The trick is, right, the difficulty is, of course, is when we start inside A. So the Q matrix can be invoked right away. So what we do, right, is for the first step, step 0 to step 1, we'll use the P matrix to analyze where you end up, right? From step 0 to step 1, uses P matrix. And then from step 1 forward, if it's outside A, you use the Q matrix. If you're inside A, of course, you're already there. Does that make sense? Or you're not there, whatever, right? Depending on the question. You understand?
I have a question about
So
that.
I'm sorry? Yeah, go ahead.
Yeah, no, this was my initial thought to the solution of where we started
Uh-huh.
3, but this would mean that it's only a valid Markov chain for 1 and beyond, not from 0 to 1.
So
Or
here's the thing,
any other.
right? That's a great question. Here, we kind of focus more on a, if you will, a calculation that's valid, right, for the whole thing. Now, notice, right, that's a great question, but the logic actually is something like this here. Basically, there's something in math, right, where we say these two numbers are equal. That's it, right? Why are these numbers equal? Well, because of certain logic behind the scene. We're not claiming, right, X is equal to W. right? So if you will, it's like a very common technique in math that we cast a problem, right, into another problem, maybe completely unrelated, right? Like a geometrical problem, right, of finding like the intersection of two lines into a system of equations. We're not claiming, right, the system of equations are lines, but whatever, when we solve them, right, we get the coordinates of the intersection of the lines. Agreed? And it's the same flavor here. We're not claiming X is W, but when we solve for W, we get the same answer as that would have given for X. Why? Because of the logic, blah, blah, blah. So to answer your question, right, the logic here, right, to use P to do the first step analysis and Q after, I guess does not claim that from 0 to whatever is a single chain, right? Or a Markov chain, as you said. Forget the word Markov, it's not even a single chain, right? But we're not concerned about that to begin with. We'll never say, oh, I'm modeling, right, a Markov chain from time 0 on. I'm just using these tools, right, these numbers to calculate the probability that will come out to be the right number, you know, as it is. Does it make sense? And why the logic is so, because, you know, the transition matrix, the transition probably goes that way. So in the end, right, what will tie all this together are just law of probability. That's it. Law of probability is the only thing that tie them together. But of course, right, the whole point here is that we have gone through many layers of, you know, we have gone through many layers of like reclassifying, remodeling, right, to make our calculation easier. And that's the technique. Is that okay?
Yeah, no, that makes total sense. 100%. Got
Yeah,
it. Thank
sure,
you.
sure. Yep. Okay, so right, long story short, right? So that's what I was telling you, right? Um, let me try to see here. I feel like, so first of all, I think there's some mistake here. Sorry, I did not take a look carefully here. This actually will be the last step analysis. Oh, no, this is correct. I'm crazy. Sorry, I'm crazy. I was advertising the example, right? Sorry, my slide is correct, but I was reading it wrong, right? I not in A, so I is the right one. Sorry, I is correct. Sorry, right? You see, I kind of explained this. This is, so I should have done the last step, but it's the same thing. So I not in A. Sorry, I was explaining the wrong one. But anyway, right? So here, for example, right, I is legit. Okay, I is legit 1, but J is not. J is 4, for example. Okay. So again, the same thing, right? Because the Q matrix does not see state J. Are we okay? But so, right, but I is okay. So you can use I, right? But you cannot use J. So here, right, the idea is to move from I to M minus 1, and then make the last transition step, which is say here. So sorry, right? I kind of did the opposite explanation to you, but so this is called a last step analysis, not first step. But it's the same thing. Do you understand the logic? I misread the status in ing, sorry. Right, so like that, right? So notice you move from I to R in the first n-1 step, and you move from R to J using the P matrix, because P, right, will see J, but Q does not, right? Are we okay? So that's last step analysis, not first step, sorry. Because the last one, the final state, is troublesome, not the first state. Any question here? Okay. Yeah, so this one, right, is I in A, right? So now I is troublesome, J is not, right? So now you look at the first movement. Like that, right? First movement and then go on. Are we okay? So that's the only logic here, right? You kind of, if the modified matrix, right, either Q cannot see, right, I or J, you use a P matrix to move you out of there, and then use a Q matrix to control the absorbing behavior.
Quick question. So
Yep.
I understand this logic, and so we're summing over all states are not in the absorbing class A. But what if along that path we were to hit some state X in the absorbing class that's not equal to J, and then from X we transition to J successfully, right? Because we might have
Are you raising a possibility here that the path this equation doesn't address? Is that what you're trying to say?
yeah, like you're missing a possible.
Okay, so let's get numbers here, right? So you want to discuss this? Sorry, you want to discuss this one, right? So here, I guess I is in the class, right? So let's say in our example, let's say I equal to 1, right? The class is 3, 4, 5, right? Sorry, I is in the class. So let's say I equals to 4, right? 3, 4, and 5, right? Let's say M equals to 10, J outside the class, right? Let's say J
We
is
said
2.
I is like what we're doing now is I is not in the class, right?
I is in the class.
Oh, this is
That's
now
why
for analysis.
this is first step analysis.
Oh, okay, sure. Sorry, I
Right,
was
that's
talking
why.
about the last. Never mind.
Okay, no, it's fine. It's fine. You want to talk about this one? You still see a process?
Yeah,
Okay,
like the
fine.
last step analysis question.
Okay,
So you
so
start outside the class.
all right. So let's say I equals to 1, right? The class is 3, 4, and 5. And let's say you want to end up at 4. Okay, and M equals to 10, right? Okay, now ask your question. What was your concern?
So like what if you go from 1 to 3 to then say some like you go to 3 at one of the intermediary points in the path, and then you
Yeah, but
eventually
no, but Q will not allow that, right?
right. But that's
That's the
why our
point.
okay.
No, that what was still
But
confusing
like
you?
that's by our construction, right? We forced the probability of going from 3 to 4 to be like
No. So again, right? The logic here is notice PRJ here. Oh, sorry, PIR here, right? Means that from step 1, step 0, whatever, right? From state 1, step to step 9, right? I guess from step 0 to step 9, right? You will end up moving from 1 to 2, or 1 and 2. That's Q to the M-1 IR due to you. Notice this is Q to M-1 I1 and Q to M-1 I2. 1, 1 and Q to 9, 1, 2. Right? That's what the Q does. it was take care for you to move from zero to time 0 to time 9, moving from state 1 to state 1 or state 1 to state 2 only. Meanwhile, avoiding 3, 4, and 5.
So logically, it's impossible to go from state 1 to another state in the class, say state 3, and then go to state 4 within 9 steps or 10 steps.
No, so again, right, be very clear here. First, we break it down to the first 9 steps. Okay, forget the last step. Last step is on its own. This is the first 9, right? Or first 10, whatever, right? First 9, yeah, okay? In the first 9 steps, because I use Q to 9, 1, 1, and Q 9, 1, 2, by construction, the chain will not hit 3, 4, and 5 in that, right? Does that make sense? Because I use Q there.
Yeah, I understand our approach. I was just wondering if the model was correct, that's all. Because we're failing to account for other possible paths, right? Through another forbidden state. That's okay. I'll think about it.
Yeah, I think in some way your question is similar to River in a way that you kind of, right, do not see clearly the difference between the calculation and the physicality of things, right? Correct. I mean, here, right, basically, yes, the chain can move from 1 to 3 to 4 and 5 during the path. That's fine. That's a possibility. But by switching to the Q calculation, again, by the logic of something like this, we have already calculated the probability that it has to avoid all those states in between to begin with. So it's a correct calculation, right? Physically speaking, the chain could still do that, but we're not modeling a single chain that does those things throughout. And that's probably what's confusing you, right? This kind of first step analysis or last step analysis requires you to basically switch to the W point of view and then switch back to the X point of view during the last step. Hence River's question about not a single chain. But that's that, right? These are two different, yeah. Mm-hmm. Yeah. All right, any other question? All right. So that's all we want to say about the thing, right? There's this one you can read for fun, but basically I want to address this because of, you know, like the problem from the last problem set, right? This has not much meaning for us, so we won't see this so much. I won't address these 2 slides, right? But same kind of logic. All right, so now the last topic, right, we want to go over is the tracking, right, a pattern of a Markov chain. As right, this is where we kind of also got some hiccup last time, right? And so the problem again, right, is that we have a Markov chain, and we suppose we start at state 0, okay? And we want to find the first time, right, that we hit the pattern 1, 2, 1, 2, right? Starting at 0, okay? And while this, right, obviously is connected to absorbing state and path probability kind of thing, the main difficulty is to construct the new Markov chain, right, to track the pattern's progression. This is the main challenge. All right. And the main challenge here is much more. So it's kind of educational, right, for you to relate back to, whoops, relate it back to, right, this one. Okay. this one, right? We also right encode new transition matrix, right? I mean, there's not a queue here. The reason is we start from an IID sequence, right? So that's why we just moved to a Markov chain. But you can kind of think of this as actually our queue in a new discussion, right? But notice it's very easy to write this down. Why would this be, right, more challenging? Right. So that's what I want to address, right? So if you remember from last time, right? So again, right, we didn't have an example from last time. So this time we'll just pick a concrete example so it's easier for us to follow. Right? This is the matrix P for X, okay? And the one thing about Y, right, that we should note is, of course, right, this is the usual progression, right? Start 1, 1, 2, 1, 2, 1, 2, 1, 2, 1, and 1, 2, 1, 2, right? So this is like, let's say, usual, right? Nothing strange here. This is the efficient, right, Markov chain modeling that we talked about. The new one is here. Because right before, we kind of just collapse it to a state 0. But that's not possible here. Okay, and that's the point. Here, it's not possible, and we want to explain why. Right? I want to emphasize, right? So basically here, right, no pattern, no progress, actually has 3 flavors, right? 3 possibilities. Starting at 0, starting at 3, or starting at 2 with not a 1 before it. Okay. So here again, right, things get confusing from any angle, but one angle should not confuse us, but it could, is the labeling, right? So the labeling of the states now, right, doesn't have a state 0 for Y, right? We call 5, 6, and 7 as a no progress state. So don't confuse that. Or actually, right, from the same point of view, right, state 1 of Y seems to correspond to, right, state 1 of X, but that's not true, right? Because state 3 may seem that way too, right? So the numbers here do not have the same meaning, right? So in fact, is, you know, we just use numerical labeling, right? Because what else can we do in, let's say, formal, right, description? But informally, right, you could kind of do 1, 1, 2, 1, 2, 1, like that, right? 1, 2, 1, 2 as a labeling of the state to make things easy to track the pattern, right? But anyway, so the new point is this, and why? Because future transitions depend on the current values of X. And different values lead to different next step behavior, right? And of course, right, you know, these are, right, 3 different behaviors that we need to separate out, okay? Grouping or not all progress to one state will lose that information, and we cannot actually, it's not going to yield incorrect probabilities, we cannot do it. All right, so this explains why 5, 6, and 7 must be there. Any question about this? Having said that, right, let's go back to here, because, right, it's very educational to compare, right, with what we have done and ask, so why is it that here we can just do a single state? Why the other one is so complex, or why the other one requires more modeling, more encoding, right? Because remember, the point here is efficient, right? Efficient encoding, right? We said you should not encode a lot, right? While it's not necessary, correct? Like this is way too much. So we reduce to this. But somehow, right, the other example, the new example we're doing, dictates that we cannot just start with one state, right? Because that will be efficient, but that's not possible. So, right, the moral here is efficient, but only so far, right? That's as it allows you to do work. You cannot be too efficient because that actually would not be possible. But right, let's ask the question. Do you see why in a new problem? Yeah.
I think last time we explored the new problem, right? So
Yeah.
we had a hard time figuring. So we first modeled it in a very simple way with the no pattern being one state. And like
Yeah.
we looked together all possible no patterns, but going from a no pattern state to a no pattern state, we couldn't figure out what that probability was because there was a lot of nuance there that we oversimplified what was really happening. So that's why we had to.
I get all that, right? I get all that. And that's the whole point. Agreed. But notice that what we say there is still waving hand over. I mean, not as not good, but saying, oh, there's a lot of nuance, blah, 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 right? Well, there's a lot of nuance, so I cannot teach you math. How about that? Right? We need to
Sure.
point out.
The specific issue
No,
is.
I'm joking. But why can't we do it here? That's the point. Why can't we do it in this problem? Right? Now, you see, that would get to the harder problem. Because if there's problem we can do and there's problem we cannot do, then saying nuance doesn't capture it. That's all I'm saying.
Idea is the time element because previously we struggled with a no pattern because one of the no patterns was saying it was because of if it was the very first two that we saw before we saw one, the time step mattered. But here the no pattern is time inhomogeneous.
Inhomogeneous?
Like sorry, time homogeneous. It doesn't matter what the time is.
Okay, you're getting closer to the idea, but say more, right? Again, why is this time homogeneous and why the other one is not time homogeneous, whatever that means?
The other one is time inhomogeneous because if you're ever at state 0 or state 3, that's just considered a no pattern. But being at state 2 currently is only considered a no pattern if it's the first state visited. So
you see, wait. You see what you're driving at?
No.
That's fine. You see the phenomenon where you're not seeing the essence of it. The essence of it actually is very simple, and actually it's been the topic we've been discussing so far. It's about dependency, period. The new problem is tracking the pattern of a Markov chain. A Markov chain has a dependency, right? That's the whole reason why we study stochastic processes, because we have dependence. And dependency is exactly what you were saying. Moving from state 0 to state 1 is very different from moving from state 3 to state 1, or state 1 to state 1 for that matter. Right? That's what dependency means. That's why we need a transition matrix. While when we were doing this problem, what were we tracking a pattern of? We're tracking a pattern of a coin flip sequence, which is an IID sequence. So there's no dependence, right? And the independence would imply that whether you were at 0 to move to 1 or whether you're at 1 to move to 1 is the same thing. Does that make sense? That's why no pattern is very easy, because no pattern moving to a new state is just that new state. Does that make sense? So again, that's the memory issue that caused the time inhomogeneity in your language, right? And that's why, because we have memory in the Markov tracking, That's why we have to keep the memory when we look at no pattern. So basically, right, the real issue is this is a Markov chain rather than a IID sequence. So that's why I need to keep track of the memory to be able to move forward. Is that okay? That's the point. So again, that theme of Markov of dependence is the reason why, right? So if anything, right, you should appreciate the difference between Markov and independence, right? Independence make things very easy, trivial, if you will. I mean, again, not trivial if you just start doing probabilities, but it simplifies a lot. When you have dependence, that's when you have to carry your memory where appropriate. Does that make sense?
Yes, thank you.
Mm-hmm. And so here, right, we'll look at the results, but here, this is, I have this at the end, right? Tracking pattern in ID sequence is easy because it has no memory. Okay. You only need to monitor the last 4 values, not depending where it came from. But in a Markov chain, it's more complex. The processor's memory, right? So that's it, right? Again, not a super big deal here in of itself. If this is just a problem we're doing, right? Because you just have to memorize the technique, whatever that means. But it's a big deal, right? In terms of you appreciating that the difference between independence and dependence, exactly, right? Is a theme throughout everywhere that we've been doing, right? I think appreciating that is a much more valuable experience. Okay, any question? All right, so now, right, having said that, then, right, the transition matrix, right? Notice in a weird way, right? Q actually is even more complex than P, right? P is even more complex than P, right? But I'm just gonna leave it here, right? Notice how we spent time deriving it last time, right? Making mistakes here and there. So I will just keep it here, right? For you to take a look for maybe 30 seconds or so, right? To see if you have any question. But so for example, right? Remember this is 1. Right? This is 1. Oh, 1, 2, 1, 2, 1, 1, 2, 1, 2, right? This is 0. This is 3, and this is 1, but not 2, right? Sorry. Wait, it's 2, but not 1, right? Okay. And this is 0, 1, 2, and 3. So I don't deny, right? Writing down this Q is a painful task. But, right, and we have to appreciate why it's painful, and this is the best we can do, right? Then we just sit down and do it.
Out
There's
of
a better
curiosity,
way. Yeah, go ahead.
if the pattern was 1, 2, 3, 4, there were no repeated
Yeah.
states, would that allow us to create a very simple no pattern state? If the possible states were like, say, 1 through 10? Like, could we resort to our simplified model?
So 1, 2, 3, let's say 1, 2, 3, 0, right? That's the pattern we want, right? Let's say, right? Is that what you're referring to?
Yeah, like there's no repetition.
So,
it's pure.
right. So what would be no pattern? So the pattern will progress from 1, right? 1 to 1, 2 to 1, 2, 3, right? To 1, 2, 3, 0, right?
Correct.
So no, you see? No. So no pattern here would still be 0, 3, and 2, but not 1 behind. Actually, still the same.
Okay.
Agree?
Yeah.
The reason is, right, how do you move from no pattern to 1? That's exactly the thing, right? And no pattern moving to 1 depends on your memory on where you are. So no, you cannot. Sorry, what the heck is this? Right, so you cannot, right? Yeah, right. The issue of memory is that you cannot. I mean, Could be. Your question is very interesting. Is there some specific pattern that somehow allows you to not worry about the memory as much, right? But I would argue that that's sort of like a not a very important question to address. The reason is, right, basically, generally, memory is still there, right? So even if we know a specific pattern, I'm not sure if it's worth memorizing, knowing those patterns too much, right?
Okay, thank you.
Sure. All right, any question about this?
Actually, to tack on to that question, would it not be
Yeah.
even more complicated because we also then have to consider 0 but not a 3 before, and then 3 but not a 2 before?
No,
That
not true, River. Because 0 but not 3 actually is at the end of the pattern, right? If you see a 0 and a 3, I see. Because you want to know. No, that's a perfect observation. Sorry, no, that's a great observation. Because yeah, no, River point out a perfect point. If you have a 3 and a 0, right, so far, are you at the last state? Or no, let's say that, right? If you know what I mean, River made up a perfect point. Sorry, mentioned a perfect point. Suppose you observe a 2 and a 3 so far, right? Are you deep in the pattern, or are you at no pattern? You understand, Kathy? So the issue of memory here actually is even worse, not better. River made a very good point. The
I
issue
understand.
here is actually is terrible. Actually, not terrible, right? Not super terrible, but yeah, no. Thank you, River, for pointing that out. Actually, it's more complex. I say it's not worse because we just have to deal with it, right? But yeah, no, great question and great answer. Absolutely. Any other question? Cool. So I think it's time to do a quiz and take a break. You know what? Since we did not do a problem, right, today, I think here, just from this transition matrix, right? Write down the Q where the class is 3.5. Okay. I think at least we did that. That's your quiz. Is that okay?
Can you
All right.
please say it
Any
again?
question? Yeah. So remember how we say, right, for a transition matrix here, we can write down the Q matrix for the state W. This one, right? For any class of A, right? And we show you the Q for when the class of A is 3, 4, and 5. So I want you to write down that Q for this matrix. Is that okay?
Mhm.
Sure. All right. So we're good. Let's take a break and we'll continue at 35, right? All right, let's continue. Is there any question? All right, so I think now let us just take a look at the problems. Okay, so the first one should be easy, right? Just probably of a specific path. So someone can tell me the quick answer here is, what the answer here is.
Point 0.2 times 0.5 times 0.2.
Thank you for that. We agree?
Yeah, that sounds right.
Yep.
All right, cool. Appreciate it. Okay. So I think, right, this is actually the same thing, right? So probably no need to redo this one, right? Just probably just another example of, Markov chain sequence, but nothing big here, right? So let's skip that. All right. So now you start to see, let's say, problems that I used to compose, right, for my students for fun, or for their entertainment on the exam. Doesn't matter, right? So okay. So first of all, right, let's look at what the question is, right? So of course it's trying to track a pattern, red, blue, and yellow, right? But the question is asking for what? If you let n be, right, the first time to see red, blue, and yellow, right? Then what is the question asking for?
The probability distribution of n.
Correct, right? It's just probably n equals to k, right? Or k is bigger than or equal to 3, right? Good. So we need to write down the transition matrix, right? I guess of Q, of the pattern tracking, right? Matrix, pattern tracking Markov chain. So what states do we have here? I guess so the Y, right? What are the states?
Well, the pattern states are R, RB, and RBY, then we have to consider how we want to treat the no pattern case.
Yeah, and what would that be?
I'm
According to
assuming
language
we
of
can't just have one no pattern
I was-
state.
right, because here actually it's kind of like the independent construction, right? Because clearly, right, there's no memory, right? So is that okay? So notice that here, right, independent could be a word, but technically speaking, it's just really a no correlation. Yeah, right. You don't have to have dependence on the. Yeah, no, sorry, it's still independent. Okay. But so let's write down a few items, right, and then we can leave the rest to you. Right. So can someone read me the 0th row? I guess I can do the last row for you, right? Can someone read me the 0th row?
My guess is 0.8, 0.2, 0.5, and 0.3.
Nope. I don't have to even think about it.
Oh
The
wait,
0th
actually,
row,
never
right?
mind, never mind.
Why would you?
Wait,
Why would you
it's
read
point,
some
it's 0.8.200.
Yeah. Okay. Do we agree?
Yeah, I agree. I'm just still a little bit confused why we have a zero state for no pattern instead of breaking it up.
Oh, the reason, right, is actually in the information given, which may or may not be that clear. But notice you don't see a Markov chain here, right? In other words, you don't
Oh,
see
so they're
how
independent.
yeah-ish, right? Exactly.
Okay,
You don't see how
understood.
I would eat the next yellow based on the previous color, right? It's the same. Agree?
Yep,
Right. Let's
100%.
do the first and second row real quick, and then we'll be done. What's the first row?
0.3, 0.2, 0.50.
0.3, 0.2, 0.50. Do we agree? All right. Second row.
0.5, 0.2, 0.3.
0.5, 0, 0.2, 0.3, you said?
No, the 0 and the 0.2 are flipped.
Oh, 0.2 and 0. Okay. Do we agree?
Yep,
Okay. Thank you, Rita. So then the answer would just be Q to the K 03, right? Correct. Oh, sorry, right? This is not the answer. Well, what should the answer be? I mean, you could have done everything here, right? And you write that down, you're still wrong, right? What's the answer? It should be this, right? Correct? Because it's equals to K, right? It's not less than equal to K. Are you okay?
Yeah, that sounds good.
All right, good. Take a look at this one. All right, so right now, one thing we probably want to pay attention to is the distinction between the first and second state, right? Because that can be mixed if we don't distinguish. So this is a B, right? But like, if we want to be careful, what do we want to say here? A not B and then a B, right? That would be state one. Do we agree?
Yep.
And then zero as no pattern, right? So again, right, let's go through this matrix and that's all we need, right? So what's going to be the first row? The 0th row.
Point 0.7.3000.
Thank you. Again, right, if there's anything you disagree with or, you want to ask.
So
do-
what's the not B here? Because this is if it's the very
Ye-
first time step, do you have a not B?
Yeah, no, that's the whole point, right? You see, that's the beauty of having the no pattern correctly, because you think about it, right? If it's the very first step, don't you get a B with probably 0.7? So you do move to state,
okay.
right? Or 0.3, whatever, right? Does that make sense? So that actually was what I was trying to say when I was looking at the big matrix, right? The tracking everything, and then move to the no progress state, right? That one actually starts to count from 0 and it counts correctly. Again, go back and see why, right? But that's the beauty of having no pattern set up correctly. It'll start even from the beginning for you. Okay. First row.
I got
I have-
0.60,
go ahead.
0.3, 0.10.
Sorry, 0.60, 0.3, 0.10. Is that right?
I have
Thank you.
that for the following row.
Oh, for second one? You mean
Yeah,
you
that's
had
what
it?
I have for the second
You had it
row.
for second row, not first row. Ah, interesting. Okay. What's the verdict here for the class?
I agree with River.
Uh-huh. So that means the first row is not what you think. So can someone tell me what the first row is, in your opinion?
0.7, 0.300.
Okay.
Yeah, that looks right.
All right. Do we agree with this for the next two rows? All right. The student who didn't get this right, are you okay
Yeah,
with
I
this?
see where I see where I went wrong there.
Okay, good. The last one, the third row.
Is it 0.6 and then, oh, wait, sorry, no, is it 0.4000.6?
Do we agree?
I had the 0.4 split between getting a B and then not getting a B. So I had 0.1 and then 0.3.
I agree with River on this one.
Yeah, River is right.
Yeah, see, that is exactly a tricky thing, right? Because you exactly, right? You could have moved from state 3 back to either state 1 or state 2, right? Oh, sorry, state 0 or state 1, right? So good. Uh, any question about this? Like again, right? I would fully admit that these things could be a bit, right? You have to pay attention, right, to the pattern. You could get it wrong, but it's okay, right? Just be patient and check back on your work. Well, the answer then will be Q to the 19, right? Because there are 19 students, I think. And then 03, right? 04. Are we okay? Any question about this? Okay. A, B, C, D, right?
Can we just do a Q matrix making C and D absorbing state and then do avoidance?
Yeah, right. This one is not pattern tracking, so right. So 0.5, 0.5, 0, 0, 1. Agree?
Yeah.
Wait, hold on. Yeah. And then the answer will be what? What's the answer here? I mean, we know we do avoidance, but see if you can write down, give me the right answer here. What would that be? Anyone? What would the right answer be?
got 1 minus sum from I equals 0 to 3, which sums from A to D, of pi
I
sub
guess
I,
it's
which
zero,
is
0 to 1, right? You said 0 to 3?
yeah, I was trying to find any way of hitting C or D. Oh, yeah.
Are you
So
using the
I was
Q
trying to,
matrix?
yeah, by using the Q matrix.
Uh-huh. But I heard you say I from 0 to 3, right? Did I hear you wrong?
I guess yeah, I guess it shouldn't be that way. I guess it should be 0 to 1.
Correct,
Or I
exactly.
guess 0 to 2, because we're going to be using the the absorbing row as 2. Would that could that work?
So hold on, right? First of all, you don't want to start at state 3 because you want to start out with state A or B, right? To begin with, agree. You only want to grade A or B papers.
Right.
So in the notation, first of all, you should only start with A or B paper. So
Okay.
making that easy, let's just do 1/4 each. Correct?
Yeah.
Okay. So
I
let's
was
start
trying
with
to
A.
do like a conjugate, so find any way of
No,
getting shouldn't do that.
agreed. Agreed. No, that's true. But you're conjugating the final state. You're not conjugating the initial state. Agree? So you should not
Right.
include
Okay.
3 in the initial state, right? You're thinking in the right track, but there's several layers here. I just want to tell you, right? You're conjugating ending up at state. Sorry, you're conjugating ending up at state 2 here, right? But you don't want to conjugate this because that's where you start. You must start there, right? So basically, here is the notation. You start at A and end at CD, or start at B and at CD. Right? These are absorbing anyway, right? That's what I mean. And you want to negate this. Agree? That's what you want. So the answer here is, right, you start at A. So you end at this, or start at B and at that, and you negate that. It's 18 because you already kind of have the first student being an A or B student. Doing,
Would
yeah, but
would it also be a correct solution to say 1/4 q to the power of 18, and then what is it? 0? Wait, no. Yeah, 0, 1
you want to
plus
deal with that, you have to do 0, 1, 0, 0, 0,
0, 0, 0,
and
1,
then
0,
1, 0, 1, 1,
yeah, and then
which is 4
1/4.
terms, right? 1/4
Yeah,
each, correct.
this is definitely a more elegant
No,
solution,
no,
but
no, it's fine.
that's
No,
still correct.
you think your thinking is exactly correct. You just list out all the possibilities of the final state, which is
Okay, yeah,
what
that's
Nick was trying to negate, right? Which is less, right? But
yeah.
yeah, no, that's correct too. All right, any question here? Okay, all right. All right, so I guess the same Q matrix, right, as before. Agree? It's the same P, I believe, right? Right? And so, ooh, this is inelegant, right? Why the heck do I have this? It should just collapse to, yeah. Anyway, I'll fix that. This is the same Q, right? And now, right, so how will we answer this question in terms of Q? You already start out with an A, right? So you will move 1 to 19. I think 1 to 19 is 18 steps, right? So 18 steps, right? You will move from here to either A, and then move from A to C, or end up with a B and then move from B to C. Correct?
Yep.
Mhm. Mm. This is, again, so inelegant. I'll fix that. All right, that's all we have for that homework, for that problem set. Any question? All right, so let me get the new slides in my iPad. Give me a few minutes and then we'll continue. All right, so lecture 8. So before we kind of talk about this, right, let me just kind of give you an idea of where we are in terms of, right, Markov chain discussion. So what we have done so far, right, what we have accomplished so far, right, is the following, or you should have a good idea of the following. The first thing you should have an idea of is what a Markov chain is. Right, and Markov property. This, right, goes hand in hand with the modeling, right, aspect of the Markov chain, right? How do we encode a state, right, into right, encode states into to make a chain Markov. Along with that, right, so that's a kind of like concepts. The technique is to compute path probabilities, including, right, the absorbing class idea, right? But I guess if you take a step back and remember the picture I drew when we first started talking about, right, Markov chain, right, with this is the time, right, and this is a state, right? So we say state 1, state 3, state 2, 1, 3, etc., right? So there are dependent structure here, right? But basically that's a typical path. So what we have done is we have exhausted, okay, I hope, or you check all ways of talking about path, all right? And so now, right, the new thing or the next step is to notice so far one way to look at this is we have looked at basically still finite horizon idea, right? We look at, right, you know, getting to a state by time 10, time 20, time 100, whatever, right? But that's still a finite horizon, right? Now we will, for the remaining, right, of the chapter, right, we'll move to a very important, let's say separate, not separate, but kind of a new idea, which more or less deal with the infinite time horizon. So now we open up, right, ourselves to looking at the chain moving on forever, right? Okay, and of course, notice that to be able to handle infinite time horizon, you must be able to, right, handle finite time horizon. If you cannot even do simple, quote, simple, right, path probabilities and forget about dealing with more complex stuff when you push things infinitely, right? That's why we spend time with these things. But when you have infinite time horizon, right? Okay, let's see what are possible questions to ask here, right? Because you want to know the theme before we start discussing them. So in an infinite time horizon, possible question that can be asked can be followed, right? The word ever or never, right, start to take on some sort of like new meaning, right? For example, let's say you start at state 1. Will you ever visit, let's say, state 10? At all? Of course, right? You know, this is a limiting question, right, of the path probability. Because we can ask the probability of moving from I to, right, 1 to 10 in, I don't know, right, 9 steps, that kind of thing, right? But the question is, will you ever go from I to J, right, at some point? Or will you never go, right? So these are still easy thing, right? This question about accessibility, right? Well, that's easy stuff, right? Kind of, because it's probably obvious by looking at a chain. Mind you, it's still not very easy if you have like a large chain, or you have infinite states, right? If you have infinite states, but it's still okay. We'll just kind of start there. But the word ever or never, right? That's kind of like the new keywords. But what else? Let's say that beyond this, right? Let's say that, of course, if it's never visiting, then who cares? But let's say among, right, the ones that it will revisit, so there will be an idea of a recurrent class. Okay. And the other one will be transient class, right? So the idea of recurrent transient class or state, right, will be kind of like natural continuation of these ideas, because basically, right, recurrent class are the ones that you keep going back and forth, right, among. The transient is basically, right, you kind of eventually get out of it and never come back, right? But among, right, the recurrent class, right, suppose you keep going revisiting, the next question is how often? Or the word frequency, right, would be another word, right? For example, right, let's say the picture I drew here, right? You visited once in 3 times, right? I don't know, in 9 steps, let's say, or 7 steps, let's say, right? So the ratio seems like 3/7. Of course, right, this is a random ratio, right? Random proportion, random frequency. As you collect more states, as you move on, right? As you travel more, this ratio for sure will change, right? Because you will move among different states. But will it settle down to a number, namely pi1, right? Or pi I, the proportion of time, right, that you visit, state I, right? And then that would lead us, or that would end up connecting to the idea of ergodic. I don't want to call it theory because that's too much. We'll just touch on a very simple part of it, but more like, let me just say, the conversions, right, of Markov chain to a distribution. So the idea is, or there's the idea of stationary distribution. These are actually 2 different ideas. People tend to confuse this. But basically the idea is if the chain itself, right, remember there's an initial distribution, right? What's the problem you start with? So if you carry that out, right, there's a pi0. Pi0 here is not probability, pi superscript 0, right? This is a distribution at time 0 of all states. And you move to pi1, right? You move to pi2, etc. So if you want, this is a distribution of x sub 0, x sub 1, right, x sub 2, right? Each of them have a distribution. Does it ever stabilize? Does it ever go to something like quote pi infinity? Right. Again, very reminiscent of like conversions of sequence and series and things like that, right? But this is a probabilistic convergence, right? So all, right, of course, you see under the theme of infinite horizon, right? Infinite time horizon. So that's where we're heading. Okay. Any question about any of the theme, I guess, that we'll be discussing? All right. So, right. So the first thing, right, we will be, like I said, right, discussing is accessibility, right? So basically, you want to know if you can go from state I to state J in however many steps, okay? So notice the n here doesn't matter. So, and notice this is a union, right? Or, but the upper bound, right, is infinite. It doesn't matter, right, how long, as long as you end up there. And so if, right, so the notation here will be I, J like this, right? J is accessible from I, right? So if not accessible, right, then the probability you ever in J star at I, right, notice this is just, probably union is less equal to a sum, right? Because of the inclusion exclusion formula. But all these are zeros, right? By assumption. So that's 0. Okay, so far. So again, right? Seems like intuitive, but there's some subtlety, right, in terms of the language that you want to pay attention to, right? P to the nij is going from I to j exactly in n steps. The word ever, right, implies a union, right? But of course, there's a connection there. Okay, any question here? All right. And so, right, then of course you can do the reverse thing, right? And say that two states communicate, right? If one is accessible from the other, right? So nothing crazy here. And really, this kind of looks a bit weird if this is more like a convention that would make things easy for us. Basically, we want to drop a class property here, or equivalence relation is the term, right? Equivalence relation. And equivalence relation requires us to say that, right, something is equivalent to itself, right? And so that's why we want to say a state communicates with itself. But notice it might seem a bit strange because, notice that it takes no step, right, to go from I to I. That's really a convention because we might think that you need to take some step, but the logic here is that you're already there, right? Kind of thing, okay? So there, this is what I'm trying to say, right? It has identity, right? It has associativity, and it has symmetry. So that's why it's an equivalence class. Now, the symmetry is obvious, right? But the symmetry, the next one is transitivity, right? Transitivity requires you to prove, right? And notice there is, right, when it comes to this state, calculation is still around, but proof starts to become an aspect here, okay? I know that to some of you, at least the word proof sounds like, a scary word, but it's unavoidable when we start discussing these things, and some problems at least will be sort of a proof idea, right? Let me explain why. The reason is, right, when you move things to infinite time horizon, you don't have a concrete calculation, okay, to do a lot of times. You only have not vaguely, you only have like inequalities, like this is positive, this is equal to 0, that kind of thing. We don't have an exact number. So you have to start getting used to like, okay, I say this, but I can write down something to back up, okay, my claim. For example, right, this claim right here is not obvious, right? So what are we claiming? We're claiming, right, let's actually, there are two parts to the claim, right? If j is accessible from I and k is accessible from j, then k is accessible from I, right? That's the part. Right? That's really the idea. Because, right, of course you can flip these things around, right? Because by symmetry of the notation, and then have, right, the communication, right? But this part right here, if I communicate with j communicates k, then I communicate, right? Again, why is this a big deal? The reason is, again, of the word ever, right? The word for some. That's if you, at Rutgers, right, it's Math 300, right, about logic. If you're not used to, if you haven't taken such a course, then you might not appreciate that logic of the word for some, right? It never dictate exactly what the number is, but just say it has to be true for some. So the proof here, right, is exactly that, right? If I goes to j for some n, and j goes to k for some m, okay, that's exactly here. There's a path here, right, of length n and length m. Then, right, the path from I to k of length n plus m, right, would be, right, so the idea is Here you go from I to J and you go from J to K, right? So the path from I to K, right, would be involving all possible in-between states. But of course, one of those, right, will go through J, which we already established that has positive possibilities. So therefore, we have that. Does that make sense? So again, right, a small thing, but just worth pointing out. And of course, right, heavily here, we rely on the Chapman-Komoroff, right, equation. And never mind this R going from 0 to infinity, right? R here is actually not time, right? This R is state, right? Basically, we just sum over all possible states. If it's finite, then the sum is finite. Okay. Any question?
When you say the sum is finite, do you mean the state space is finite?
Yeah, like I'm saying, this
Sum over all
gives you the
possible.
impression. Yeah. This might, I don't want to give the wrong impression that you have to have infinite state space. This whole, right? If you have finite state space, it will just become a finite sum, right? I just want to point that out because time is already infinite here. And there's a very big danger of folks reading time into space and space into time. Believe me, that could happen with all the notations, right? So I just want to point that out, more or less, right?
That makes sense.
Okay.
Thank you.
Sure. All right. So I think we're right on time. So let's stop here, right? And we'll continue with this topic on Friday. Okay.
Thank you.
Thank
Sure.
you, Professor.
Thank you, Professor.
Yeah.
Yep.
Thank
Thank
you,
you.
Professor.
Yep.